This is a molecular modeling kit. You can use it in senior biochemistry to make your name. This is heme. Actually, it's 4 amino acids joined together: histidine, glutamic acid, and asparagine. So this whole molecule will be called histidyl-glutamal-asparagine. But let's go with heme using the one-letter naming system for amino acids. Anywho, at a more junior level, you can use these modeling kits to show molecular geometry, basically the shapes of molecules. Now this is using the VSEPR theory, the valence shell electron pair repulsion theory. This theory assumes that the electron-electron repulsion between atoms bonding to another central atom will want to keep the non-central atoms as far away from each other as possible. The shape of the molecule will depend on the number of atoms bonding to the central atom and also the central atom's number of non-bonding pairs of electrons. Now, non-bonding electron pairs occupy one position of the normal geometry. But because non-bonding electrons are held closer to the central atom, the other bond angles will be slightly distorted away from the non-bonding pair. So let's have a quick look now at some molecules that I've made. Here we go. This is CO2. Black tends to be carbon in these modeling kits, and red is oxygen. So we have a CO2 molecule. Now, firstly, we can note that actually CO2 is double bonded. There's a double bond between the carbon and each oxygen. But in terms of the molecular geometry, the shape of the molecule, we can see that it is linear. Now, the bond angles from one bond over to another bond, that bond angle, being a linear molecule, is going to be 180 degrees. If there were one non-bonding pair on the central atom, that would produce a 2-atom molecule that can't be anything but linear. Great, thanks CO2. Let's step it up. Let's look at a central atom with 3 other atoms around it. This time, the bond angle from one bond to the next, given that it's 360 degrees all the way around divided by 3, that bond angle is going to be 120 degrees. Now the molecule is flat, and the geometry is called trigonal planar. So this is a trigonal planar molecule. An example would be boron trichloride. Now, if we removed one of those atoms, the non-central atom, we would come to something like this sort of paddle-shaped thing here that indicates a lone pair of electrons, a non-bonding pair of electrons. So what we have here is sulfur dioxide. Now, we can see that the bond angle here is about 120 degrees because it's like there were 3 things sticking off. But remember, this lone pair of electrons is closer to the central atom, and because of electron-electron repulsion between these electrons and those bonding electrons, and these electrons and these bonding electrons, the bond angle will be pushed around a bit. So the bond angle will be actually a little bit less than 120 degrees. Oh, and I should probably mention this is an angular molecule or bent molecule. Okay, so that's 3 spaces around the central atom. What about 4 spaces around the central atom? Well, here are a couple of examples. The one on the left is methane, a carbon with 4 hydrogen atoms around it. And the one on the right is carbon tetrachloride, a carbon with 4 chlorine atoms around it. Now, let's just get rid of one of them. That's big in the video, so we'll use this one. This molecule is tetrahedral in shape. Now remember, tetra meaning 4. The way I remember it is it kind of has 4 faces. Well, none there, but you could put them on. Like you could put on one here. There's one face. One at the back here, one here at the front, and of course one underneath for the base. So it's kind of like a pyramid, I guess. So tetrahedral molecule. Now the bond angles, with every bond trying to get as far away from every other bond as possible, that leads to a bond angle of 109.5 degrees. If we have a lone pair, that will be something like this. There we go. Now this is ammonia, NH3, 1 nitrogen and 3 hydrogens, but the nitrogen actually has a lone pair of electrons up the top. So those electrons will be pushing these other 3 bonds down, and the bond angles will therefore be slightly smaller than the previous 109.5 degrees. They will be about 107 degrees, because remember, those lone pair of electrons are pushing the other electrons from the bonds further away due to electron-electron repulsion. Now, what if we had 2 regions where we had lone pairs of electrons? Well, here we go, 2 lone pairs of electrons, and you know what I'm going to do is actually just get rid of those. There we go. This is the water molecule, and we can see the shape of the water molecule. It is bent. All right, water is a bent molecule, or angular might be a better way to describe it. So water is an angular or bent molecule, and this is because it has 2 lone pairs of electrons. What we could do is stick something like this in, just to represent lone pairs of electrons. So we can still see that there are two places where there are unbonded electrons, non-bonding electrons. Now, the electron-electron repulsion between these and these bond angles are what forces the bonds closer together. So the bond angle in this case, in water's case, is about 104.5 degrees. So it's even a little bit smaller than when we just had 1 lone pair. When you have 2 lone pairs, the bond angle gets just that little bit smaller. Let's move up to a central atom with 5 other atoms around it. Here we go. This is phosphorus pentachloride. Now, I might just move my camera away a little bit and try to up the angle. There we go, so we can see it because this is a bigger molecule. Right, so what we can see, hopefully, is we have 2 polar atoms up above and 1 down below. So that's in a straight line. But then around the side, we have 3 what we call equatorial atoms. Okay, so we have a central atom with 5 other atoms around it. 3 of those are equatorial atoms. Now, the bond angle between those equatorial atoms will be 120 degrees because, 360 all the way around, divvy up by 3. So 120 degrees, and 90 degrees between the polar atom and the equatorial atom. So there we go, phosphorus pentachloride. Oh, actually, I didn't say the name of this shape. This is trigonal bipyramidal. Okay, so the trigonal bipyramidal structure there. Now let's just have a lone pair. Here we go, we have 1 lone pair now. This is sulfur tetrafluoride. Now, we still have our polar atoms, 180 degrees between them. But we've actually removed an equatorial atom. Okay, so the equatorial position is where we have our lone pair. Now, the bond angles will still be 90 between the polar and the equatorial, and it will still be 120 here between the equatorial atoms. So this shape is often called a seesaw molecule because if we turn it a bit, let's just get rid of that. Look, we've just made a seesaw. So there we go. A trigonal bipyramidal structure with 1 lone pair leads to this seesaw structure. Now, what if we had 2 lone pairs? Well, let's just pull off this. Now, what you'll note is that I just pulled off another equatorial position. We still have the 2 polar atoms, and we've only left with now 1 equatorial. Okay, so that would be a lone pair of electrons there, and another lone pair of electrons there. And this is because the 2 non-bonding pairs will both take equatorial positions, creating this T-shaped molecule. You could look at it like this. There we go. That's kind of nearly a whole T, just missing this other arm. Or you could just turn it like this. There we go. There's your capital T. So this is a T-shaped molecule, and the 3 bonding atoms are at 90 degrees. An example would be bromine trifluoride. So here we go, bromine trifluoride. If we had another lone pair or another non-bonding pair of electrons, again, it's from the equatorial position. So what are we left with now? Just the polar atoms, so it's a linear molecule, and the bond angle obviously is 180 degrees. Right, let's step it up one more time. A central atom with 6 other atoms around it. This will produce an octahedral molecule. Now, remember with the tetrahedral, tetra 4, and we could sort of see 4 faces of it, or where those 4 faces might be to form that pyramid shape. Well, octa, we're talking 8, aren't we? Because, I'm going to show this. There's one there, one at the back, one here, and of course the same thing on the bottom half. So 4 faces up top, 4 faces below. This is an octahedral molecule. The bond angles are all 90 degrees. An example of this is sulfur hexafluoride, which you see in front of you now. One non-bonding electron pair, ta-da, will cause a shape called a square pyramidal molecule, because look, ta-da, there you go. It's like a pyramid with a square base instead of a triangular base. So this is a square pyramidal molecule. An example would be chlorine pentafluoride. The bond angles are still 90 degrees. Now, if there are 2 non-bonding pairs, they actually take up positions opposite each other. So if we pulled off this bottom one, we have to pull off this top one now. Here we have our little ninja star, the little flat molecule there. This is actually called a flat square planar molecule. Okay, planar because it's flat. It's 4 corners, so it's making a square. So it's a flat square planar molecule with bond angles still being 90 degrees. An example would be xenon tetrafluoride. Now, further non-bonding pairs will result firstly in a T-shaped molecule and then in a linear molecule. However, this many non-bonding pairs is very rare. So there you go. That's playing with a molecular modeling kit and looking at shapes of molecules, molecular geometry, using the valence shell electron pair repulsion theory, often shortened to VSEPR theory. Well, that's the video done. If you liked it, brilliant. Hit the like button and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.